So we all know what it feels like to push something, right? To make an effort. And we see something happen. It moves. But what's the actual physical connection between that push and the motion we see? It's something we feel every day, pushing a swing, lifting a grocery bag, but physics gives us this incredibly precise way to define it. And that's exactly what we're going to break down today.
So, let me ask you this. What in the world connects the simple act of pushing a swing in a park to the mind-boggling speed of a satellite whipping around the Earth? I mean, they seem like they're in completely different universes, right? But believe it or not, the physical rule that governs both of them is exactly the same, and that's the mystery we're here to solve.
Okay, here's our game plan. We'll start with the basics, the push and the motion. Then we're going to define what work really means in physics. And trust me, it's not what you think. We'll meet its partner, kinetic energy, and then, this is the big one, we'll see how they're linked with the work-energy theorem. Finally, we'll see if this rule breaks when things get a little more complicated.
All right, first up, the push and the motion. Let's start right at the beginning.
This seems super obvious, right? We put in some effort, that's a force, and we get a result. The thing moves, or it changes its motion. Simple. But here's the thing. Physics isn't happy with just it moves. Physics wants to know how much it moves, how fast it's going, and exactly how that result ties back to the push we gave it. That precise link, that's what we're after.
Okay, that brings us to our first big concept, defining what physics calls work. And just a heads up, this is where things get a little weird, because it's probably not what you're thinking.
In our everyday lives, work is, well, it's thinking really hard or stressing about a deadline. Heck, even just standing there holding a super heavy bag feels like a ton of work. But in physics, nope. You could hold a 100-pound dumbbell perfectly still for an hour, sweating, muscles screaming, and a physicist would walk by and say, "You've done zero work on it." Zero! How is that possible? Well, it's because physics work has a very strict two-part rule. You have to apply a force, and the object has to move some distance in the same direction as that force. Both have to happen. No exceptions.
So here's the official definition. Work is the energy that gets transferred to or from an object when you apply a force over a distance. But honestly, the best way to think about it is like this. Imagine every object has an energy bank account. Work is the transaction. It's the deposit of energy you make when you push something, or the withdrawal you make when you slow it down.
All right, so if work is the transaction, what's in the account? Well, that leads us to the other major player in this story, the energy of motion. Let's meet kinetic energy.
Okay, this one is way more intuitive. Kinetic energy is just the energy an object has because it's moving. That's it. If it's moving, it has kinetic energy. A car parked on the street, zero kinetic energy. That same car flying down the highway, a lot of it. The faster it goes or the heavier it is, the more kinetic energy it's got. So let's bring back that bank account analogy. If work is the deposit or the withdrawal, then kinetic energy is your current account balance. It's the actual, tangible amount of motion energy that the object is holding right now. It tells you the state of its motion. Okay, deep breath. This is it. This is where it all clicks into place. Let's talk about the work-energy theorem, the ultimate connection. So just to recap, we've got work. That's our action. It's the process of transferring energy to an object. It's our deposit.
And then we've got kinetic energy. That's the state of the object. It's the energy it has because of its motion. That's our balance.
So this leads us to the biggest question of all, right? How exactly does the transfer of energy, the work we do, change the object's state of energy? It's kinetic energy. In our analogy, how does the deposit change the balance?
And the answer is one of the most beautiful and powerful rules in all of physics, the work-energy theorem. It simply says that the net work you do on an object is equal to the change in its kinetic energy. W equals delta KE. And when I say equal, I mean exactly equal. It's not an estimate, it's not a close enough, it's a perfect mathematical lock.
This is where our bank account analogy just sings. It's perfect. The amount of work you deposit is exactly how much the balance of kinetic energy goes up. It's a perfect one-to-one relationship. If you do 10 joules of work pushing a box, its kinetic energy increases by precisely 10 joules. That is the fundamental link between your effort and the motion that results.
Okay, that's great for a nice, steady push. But what about in the real world, where things are messy? What happens when the force changes? Does this perfect little rule still hold up?
Well, think about something like a rocket engine, where the thrust changes, or even just stretching a rubber band. The force isn't constant, right?
So how do you calculate the work? Well, physicists have this really clever trick. They basically hit the pause button over and over. They break the entire path down into a bunch of tiny, tiny little sections. And in each one of those microscopic sections, the force is pretty much constant. So they calculate the tiny bit of mini work for that one section, and then the next, and then they just add all those little pieces up to get the total.
And here's the beautiful part. What this proves is that the work-energy theorem is incredibly robust. It still holds true. Even with a crazy changing force where you have to add up all those little bits of work, the grand total, the total work you calculated, is still perfectly equal to the total change in the object's kinetic energy. The rule just works, no matter what.
So let's wrap this all up. What's the big picture? First, work in physics isn't just effort. It needs both force and distance. Second, kinetic energy is just the energy of motion. And most importantly, they are linked by this incredible principle, the work-energy theorem. The work you do on something is not just related to its change in motion, it is equal to its change in kinetic energy, delta KE. And this fundamental law of the universe holds up even when the forces get complicated. So we've figured out that work is how we transfer energy to make things move. But that kind of opens up an even bigger question, doesn't it? If work is just the transfer, where does the energy itself come from in the first place? Well, that is a story for another time. Thanks for joining me.